In this example, we want to find the rectangular equation by eliminating the parameters and then sketch. Here we have a parametric surface, r in terms of u and v equals 3 cosine v cosine u, I plus 3 cosine v sine u j plus 5 sine v k. We do want to eliminate the parameters u and v and come up with the resulting rectangular equation that uses only x, y, and z. We can begin by letting x equal the first component, y equals the second component, and z equals the third component. So we have x equals 3 cosine v cosine u, y equals 3 cosine v sine u, and z equals 5 sine v. We'd like to eliminate the parameters. Notice that all three of them have a v in it, but only the first two have a u in it. So let's begin by solving for cosine u in the first equation and solving for sine u in the second equation, so that we can use the identity cosine squared u plus sine squared u is equal to 1. So if you divide x equals 3 cosine v cosine u by 3 cosine v, then you can find that cosine u is equal to x divided by 3 cosine of v. Divide the second equation by 3 cosine v to get the equation for sine u equals y divided by 3 cosine v. Now we can substitute both of those into the identity cosine squared u plus sine squared u equals 1, and we can eliminate that parameter u. Cosine u is x over 3 cosine v. So if we square both sides, we get cosine squared u would be x squared over 9 cosine squared v. Sine squared u, if you square both sides here, that is going to equal y squared over 9 cosine squared v. And that equals 1. We've eliminated the parameter u. If we multiply both sides of this equation by 9 cosine squared v, we can then find that, or even actually let's not do the 9 here. Let's multiply both sides by cosine squared v, and then we get the equation x squared over 9 plus y squared over 9 is equal to cosine squared v. Now I want to use the identity, the trig identity that involves v with the cosine. If we use the identity cosine squared v plus sine squared v, we know that is going to equal 1. Now we have already solved for the cosine squared v here, and we're going to use this equation up here to solve for sine v. We'll do that by dividing both sides by 5, and that's going to give us sine v is equal to z divided by 5. So using now this equation and this, we're going to substitute it into this equation. That is going to give us cosine squared v. We've solved for cosine squared v over here. That's going to be x squared over 9 plus y squared over 9 plus sine squared v. We've already solved here for sine v. If you square both sides here, sine squared v is z squared over 25, and that is going to equal 1. We have eliminated both parameters u and v from this equation, so that we end up with the rectangular equation in this form. Now, hopefully you recognize this as an ellipsoid, where all the cross sections are all the traces are ellipses. So to sketch this in 3 dimensions, you're going to go 3 units in the x direction. It's our x-axis. You're going to go 3 units in the y direction. And you're going to go 5 units in the z direction. Okay, the traces are ellipses. Alright, so this is the sketch of the ellipsoid using the rectangular equation, x squared over 9 plus y squared over 9 plus z squared over 25 equals 1. We started off with the parametric surface, r in terms of u and v, and used some algebra and identities to eliminate the parameters u and v. Okay, in this example, we want to find a vector valued function for the surface. We can now introduce those parameters u and v so that we can come up with a parametric surface, r in terms of u and v, where is equal to some x in terms of u and v I, some y in terms of u and v j, plus z in terms of u and v k. One way, there are many, many ways of doing this, but one way is by introducing those parameters u and v. You can let x equal u, you can let y equal v, and then you can solve for z and make the substitutions. If x plus y plus z equals 6 and you solve for z, z equals 6 minus x minus y. And if you've introduced the parameters u and v, you can then make those substitutions here to get z equals 6 minus u minus v. So our vector valued function for the surface, coming up with an equation r in terms of u and v, we can write this as r in terms of u and v is equal to, we can replace x with u, that's going to be ui, plus vj, plus what our z equals 6 minus u minus v, all of that k. So this is a vector valued function for the surface. Also, if you recognize the original form of the equation, this is the equation of a plane, and you can sketch the plane by finding the x, y, and z intercepts. A quick sketch would look something like this. In this case, the x, y, and z intercepts are all 6. You can connect those intercepts using lines, and this is just a portion of the infinite plane that is represented by this vector valued function. In this example, we want to find a vector valued function for this surface. 4x squared plus y squared is equal to 16. This equation only has an x and a y in it, so when you create the surface in space, z can be anything. And if we were to do a quick sketch of this surface, the xy trace is an ellipse. In fact, you can divide everything by 16 to get it into the form of an ellipse, where you have x squared over 4 plus y squared over 16 is equal to 1. So that means you would go 2 units in the x direction and 4 units in the y direction. X-axis, your y-axis. There's no z in the equation, so the surface is parallel to the z-axis. The trace here is an ellipse, and we can draw another ellipse parallel, and Draw vertical lines. This represents a portion of the surface. Okay, now we want to come up with a vector valued function r in terms of u and v, where you have r in terms of u and v is going to be equal to some x in terms of u and v I plus some y in terms of u and v j plus some z in terms of u and v k. One way to do a conversion here is by using, especially with ellipses and circles, is by using those trig identities, cosine squared u plus sine squared u is equal to 1. So if we know that the identity cosine squared u plus sine squared u is equal to 1, and we recognize that this is in the form here of something squared plus something squared equals 1, then we can equate these. We can say x squared over 4 is equal to cosine squared u, and we could say y squared over 16 is equal to the sine squared u, and come up with the equations that way. So if we let x squared over 4 equal cosine squared u by setting these two to be equal and taking the square root of both sides, you get x over 2 equals cosine u, and then solve this for x, and you get x is equal to 2 cosine u. Okay, in a similar way, you would find the equation for y. Set y squared over 16 equal to sine squared u and solve that equation for y. Okay, I've moved things around here a little bit. Let's go ahead and set the y squared over 16 to equal the sine squared u. If you take the square root of both sides, you get y over 4 equals sine u, and multiply by 4 to get y equal 4 sine u. And notice in this equation we don't have any z, so we can let the parameter let z equal the parameter v. Since we've already used the u for the x and y, we can introduce a parameter v in the z. So this parametric surface, r in terms of u and v, is equal to x. That's going to be 2 cosine u I plus y, which is 4 sine u j, plus your z, which is your vk.